is about phasors. Yeah, it's about phasors. When when the signal, the AC signal, has the same frequency, the forcing function, the forcing signal has certain frequency omega, and the response also has frequency omega. So then what matters is actually the change in the amplitude, as well as the phase change of the phase of the output, because the frequency will remain the same. Yeah. So when and at that condition is where phasors are being used. Okay. So the essential condition for using phasor notation is that all independent sources are in sinusoids of the same frequency within that circuit. Because of a source superposition, we can consider a single source like this: small ut equals to um, the amplitude, multiplied to cosine omega t plus theta. Omega is the radial frequency, and theta is the phase. Then this is put, the source is put into a network. The steady state response of any circuit variable in the network will be of the form small yt equals to ym times cosine omega t plus phi. Okay. So here we see that the omega does not change. In that particular case, then we could have a shortcut. The small ut here is expressed in the complex notation as times exponent j, and in parentheses is omega t plus theta, while the response, the steady state response from the circuit, is expressed as yt equals to ym, the magnitude here, exponent j omega t plus phi. However, we know that actually when we use complex notation like this, there is the imaginary component, the j sign. So what we take is only the real part of this expression. So the real of this exponent j omega t plus theta equals to the real part of this ym times exponent j omega t plus phi. So what now we try to uh, re-express again exponent j omega t plus theta. In this case, times exponent j omega t plus theta equals to and this becomes multiplications of exponent j theta multiplied to exponent j omega t. Then in this case, the similarly also we can do the same with the ym. The y equals to y. This one equals to ym exponent j phi exponent j omega t. Since the exponent j omega t are the same in both sides, then we can cancel it. We do not need to take them into account. So what matters now is only the phase and the amplitude. The u, the, the magnitude of the single source, the u equals to large times exponent j theta, and the response will be y equals to ym exponent j phi. So, so this is a shortcut in notation. Instead of writing then u equals to exponent j theta, we could express this in a notation called its phasor, where it is expressed as small u here, and a phase angle of theta. Okay, so this shows basically a sinusoidal function with a magnitude of and phase theta. The frequency is basically already known there from the problem. And because we only take into account the magnitude and the phase angle, because that those two are the one that will change in the steady state response. The frequency will remain the same. Here we also accept angles in degrees. Large phase angle theta is the phasor representation of cosine omega t plus theta. So be careful here. This is the representation of cosine. So if later we are dealt with sine, then we have to add negative 90 degrees, additional negative 90 degrees to express it as cosine. So the small ut here equals to um cosine omega t. Yeah, from here plus theta. The u here, the magnitude u equals to um phase angle theta, and the y equals to the response y equals to ym, the magnitude, with phase angle phi. So the yt, the final complete function of the response of any circuit variable within that from that network is yt equals to the real form of ym cosine omega t plus phi. Okay. But in the phasor notation, this is hidden. Yeah, it is hidden because it is assumed to be not, and it is assumed that it will not change. The frequency does not change. That is why this is steady state analysis. Later we will learn about frequency dependent response in different chapter. Develop efficient tools to determine the phasor of the response given the input phasors. Okay. Okay, let's consider this circuit. Yeah, we have here a circuit of resistance connected to an inductance and a source, a voltage source Vt equals to the Vm magnitude cosine omega t is connected to it. Current is flowing through the network. So V here is expressed as the magnitude Vm with a phase angle of 0, and the small v equals to this V times exponent j omega t. So because this represents the exponent j theta, and theta here is 0. Okay, this V, this one, multiplied to exponent j omega t, the frequency domain. The current I is expressed as the I large, I capital equals to Im with the phase angle of phi. The phase angle, while the small current here, the signal is this I multiplied to the frequency component, the exponent j omega t. Yeah, this part. Okay, so basically this, if we express it, this one, basically this is comes from Im exponent j phi. Okay, well this one Vm exponent j 0 at 0 phase angle. So from this circuit, then we draw the using KVL, LDI P dt plus RIT equals to V, the voltage source. So then we can insert this component, yeah, this component, the I, the small it here equals to the large I exponent j omega t, differentiated against time becomes I j omega times the large I exponent j omega t plus R I exponent j omega t equals to the v, small v here, which is large V exponent j omega t. So here you see that the term exponent j omega t exists in each of the uh, we call it each of the term here, yeah, either on the left hand side of the equation and right hand side equation, so they can be cancelled from each other. So this becomes j omega li plus ri equals to v. Yeah, the j omega t cancel to each other. This cancel. This has become the term of phasor has this j omega li r equals ri equals to v. This is in capital, so which can be then be expressed later as this one, yeah, Vm. So I, the current will be equals to V divided by j omega L plus R. So phasor can be obtained using only complex algebra. No need to use anything else. Okay, so yeah. So this one, then this circuit then can be expressed, yeah, in terms of phasor in KVL. One will have then j omega Li plus Ri equals to the voltage from the voltage source. The current equals to voltage divided by R plus J omega L. So you see here that we can easily find the current using a simple complex algebra, not that simple maybe. So we don't really need again to take into account this exponent omega t. So we will develop a phasor representation for the circuit that will eliminate the need of writing the differential equation, because this is now in steady state analysis. It is essential that you know how to move from sinusoids to phasor representation. For example, if we have a cosine omega t plus theta, then this is represented by phasor as a, this angle of plus minus theta, depending on this plus minus. If it were a sine omega t plus minus theta, be careful, and from the definition, that phasor is representing cosine function. So if the function is sine, then you have to put the additional phase angle of minus 90 degree, because a sinus wave lags a cosine wave by 90 degrees, or to say it in different way, cosine wave leads sine wave by 90 degrees, or by pi over 2. So for example, if we have here phi t equals to 12 cosine 377 t minus 425 degrees, you can express this only from the amplitude and the phase angle only, the phase angle of minus 425 degrees. If we have yt equals to 18 sine 2513 t plus 4.2 degrees, and when you want to express it as phasor, it becomes 18 with phase angle of minus 85.8 degrees, because this 4.2, then you subtract further with negative 90 degrees. If given frequency equals to 400 hertz, then if in the problem it is given that voltage 1 is 10, magnitude with 10 with phase angle of 20 degree. So when you express it as a normal cosine function, it becomes V1, small V1 t equals to 10 cosine 2 times 400 pi, right? 2 times this frequency, which becomes 800 pi t plus the angle, phase angle, 20 degrees. If it were V2 equals to 12 with phase angle of minus 60 degrees, if you want to re-express it as cosine, as sinusoidal function, it becomes V2t equals to 12 cosine 2 times 400, 800 times pi t minus 60 degree. Okay. We can combine phasors using the rules of complex algebra. So it means if we multiply V1 with an angle theta 1 times V2 with an angle theta 2, this becomes V1, V2 angle of theta 1 plus theta 2. Yeah. So if you are still confused, we can graph this. So basically, this is V1 exponent j theta 1. This is multiplied by V2 exponent j theta 2, right? So this becomes V1, V2 exponent j theta 1 exponent j theta 2. So this equals to V1, V2 exponent j from complex algebra from j theta 1 plus theta 2. Re-expressing back into phasor, so this equals to V1, V2 with an angle of theta 1 plus theta 2. Okay, so I hope it's understandable. Then if instead of multiplication we have division like this, then it is just the plus just become minus. V1 with a phase angle of theta 1 divided by V2 with the phase angle of theta 2, equals to V1, the magnitude, V1 divided by the magnitude V2, and the phase angle will be theta 1 minus theta 2. Okay, so expressing in phasors really simplify the calculation. So for example, if we have resistor only, The Vt here equals to R times IT, yeah, the small it. The Vt is expressed as magnitude Vm exponent j omega t plus theta equals to R with large Im exponent j omega t plus theta, yeah, for the current. So then the exponent j omega t can be cancelled from both sides. So Vm exponent j theta equals to Ri m exponent j theta. Or if we cancel again the exponent j theta from both sides, then it means V equals to Ri. So this is the phasor representation for a resistor. V equals to Ri. If we draw it in the phasor diagram, which we will complex diagram, in the complex diagram, we will discuss later also in more detail in the later section. So in the real, the angle, the phase from the real, positive real, is the same for both voltage and I. So the theta V, the phase angle of the voltage, will be equal to the phase angle of the current, theta I. Okay, only then the magnitudes are different, yeah, by a ratio of R. Phasors are complex number. The resistor model has a geometric interpretation. The voltage and current phasor are collinear in resistive circuit like this. In terms of the sinusoidal signal, this geometric representation implies that the two sinusoids are in phase. In phase means that there is no phase difference between the two sinusoid function. Only the magnitudes are different. Like this, V, the I equals to voltage divided by R, but the phase remains the same. Theta V equals to theta I. So this is for resistor circuit with resistor. What about if for inductor? So if we connect inductor to voltage source, yeah, Vt equals to L di dt, like this. So Vm exponent, we express Vt here as the magnitude Vm exponent j omega t plus theta. Here L di dt, right? The I we change into Im exponent j omega t plus phi, yeah, the new phase. Okay, so this, the derivation of this towards with respect to time becomes j omega, yeah, here j omega Li, j omega Li m exponent j omega t plus phi. So the component exponent j omega t can be cancelled again from both sides of the equations. I hope I don't need to derive it in more detail. So please, this is just from complex algebra, yeah, which you can review again from mathematics. So this becomes then Vm exponent j theta equals to j omega Li exponent j phi. Okay, so the voltage equals to j omega Li. Voltage equals to j omega Li. The V here equals to this. The large V here equals to Vm exponent j theta. I here equals to Im j exponent j phi. Okay, so connecting this one becomes this, and this one becomes this. Okay, so V with phasor, yeah, equals to j omega Li. The relationship between the phasors is algebraic. For the geometric view, we can use the result. Yeah, J can be expressed as basically exponent J 90 degrees, right? Exponent J 90 degrees equals to cosine 90 is 0. So the real part is 0 plus J sin 90 degrees or plus 1J. Or if we express it in phasor, the magnitude is 1, the phase angle is 90 degrees. Okay, so this is equivalent. This is in complex form. This is in phasor form. This is in Euler form. Exponent j 90 degrees. Hence, then the phi here since since there's J here, the J can be re-expressed as this one, 190 degree, or exponent J 90 degrees. If you want to express it, re-express it in phasor, this become angle of 90 degrees. So V equals to omega Li with an additional of angle 90 degrees. What does it mean? It means the voltage leads the current by 90 degree, or the current lags the voltage by 90 degree. The voltage leads the current by 90 degree. So this theta V, the phase angle of the voltage, equals to the phase angle of the current plus 90 degrees. Okay. So remember that in sinusoids, this means two waves having the same frequency, each one having different amplitude. The Vt will leads the current, the It, sinusoids, by 90 degrees. So the difference here is 90 degrees. For example, we have inductance of 20 millihenry. The voltage source equals to 12 cosine 377t plus 20 degrees. Find the current I. So I will be equals to j omega L. I will be equals to voltage divided by j omega L. Here, okay, the voltage here is expressed from only from the amplitude and the phase 20 degrees. 12 is bracketing 20 degrees. The current equals to, yeah, from here. Then the current, which one? Yeah, from here, the current equals to voltage divided by j omega L. So if it is like this, or the current, if we substitute the voltage with the value, so this is equals to 12 with a phase angle 20 degrees divided by omega L. And J becomes 90 phase angle of 90 degrees, right? From this relationship. So if we divide an angle, so this becomes minus, yeah, from the complex algebra. So the current will be 12 divided by omega, which is 377, multiplied to 20 millihenry here, and the angle becomes, the phase angle becomes 20 degrees minus 90 degrees. Okay, the phase angle in the denominator becomes negative. This is from the complex algebra, if you want to derive it in more detail. So the current, the in sinusoidal format, sinusoidal form, this becomes 12 divided, this is the magnitude, 12 divided by 377 times 20 times 10 to the power of minus 3 cosines 377t negative 70 degrees ampere. Okay, it's clear, yeah? Okay, now what about capacitor? When we connect a capacitance to the voltage source, the capacitance law states that the current equals to C dV dt. Okay, so from using Kirchhoff voltage law, yeah. Also the current here, Im exponent, the current is Im exponent j omega t plus phi equal to C dt of the voltage. The voltage is Vm exponent j omega t plus theta. Okay, then you can express this. The j omega t can cancel each other from both sides. So this becomes Im exponent j phi equals to this one, the j omega c, yeah, exponent j theta. Actually, there should be Vm here, yeah. So there should be here Vm. This is forgotten. Yeah, should be Vm there. So then from there, this is I basically, I phasor, and this is Vm exponent j theta is also V phasor. Yeah, so j omega c phasor. So here you see that the current now leads the voltage by 90 degree. Okay, I equals to j omega c v. The current equals to omega c, and we replace j here with a phase angle of 90 degree. So that the current leads the voltage by 90 degree. or the voltage lags the current by 90 degrees. And the theta I equals to theta V plus 90 degrees. In a capacitor, the current leads the voltage by 90 degrees. The voltage lags the current by 90 degrees. So here, if we draw it, the current is in front of the voltage. Current already here, the voltage still here. Okay, so the relationship shown in the sinusoidal graphs. For example, we have capacitance of 100 microfarad connected to a voltage source of 100 cosine 314t plus 15 degrees. Find the current. So the current will be equals to, so omega is 314, the voltage is 100, the magnitude, and the phase is 15 degrees. Current here equals j omega CV. Yeah, current equals j omega CV. So equals omega C times the angle 90 degrees times the voltage 115 degrees. So here we see that the phase angle of the current becomes 90 degree plus 15 or 105. Yes, the current equals to 314 from here, the omega times 100, the capacitance value, 100 microfarad, 100 times 10 to the power of minus 6, times 100 of the voltage with an angle of 105 degrees, 90 plus 15 degrees. If we want to express it again in sinusoidal form, this becomes IT equals to 314 in ampere. So this times this is 10 to the power of 4, and this is 10 to the power minus 2. 3.14 cosine omega t 314t plus 105 degrees. Okay, it's clear, yeah, how the circuit in steady state analysis of AC behave for resistor, for inductor, and capacitor. Let's now find the voltage across this inductor when we have a 0.05 Henry inductance. The current is 4 ampere with a phase angle of minus 30 degrees. The frequency is 60 hertz. Omega is 2 times pi times f, so 120 pi. The voltage equals to J omega Li. J omega Li. Then we substitute the numbers. So this one 120 pi omega, yeah, times the inductance 0.05 times J becomes 1 with an angle of 90 degree times current. The current is 4 with an angle of minus 30 degree. So the phase angle later of the voltage becomes 90 minus 30, 60 degrees. Okay, so this, the magnitude becomes this value times 4. 4 times 0.01 is 0.2. 0.2 times 120 is 24. 24 pi with an angle of 90 minus 30 is 60 degrees. And we want to express it in sinusoidal function. This becomes 24 pi, the magnitude cosine 120 pi plus 60 degrees. Now, this is an example for the circuit with capacitance. If we have capacitor of 150 microfarad, the current is 3.6 with an angle of minus 4, phase angle of minus 145 degrees ampere, yeah? And frequency is 60 hertz. Find the voltage across the capacitor. So the omega is 2 times pi times f here, 60 hertz, times 2 is 120 pi. Then from the formula that we have derived in the previous slide, the current equals to the j omega c times v. Yeah, the current leads the voltage by 90 degrees. Or voltage equals to the current divided by j omega c. Divided by j omega c. So we insert the values. Current is 3.6 with an angle, phase angle of minus 140 degrees divided by J here becomes 1 phase angle of 90 degrees. Omega is 120 pi, 120 pi. C is 150 microfarad. From here, the magnitude will be here, 3.6 divided by 120 pi divided by 150 microfarad. The phase angle difference will be minus 145 degrees minus 90 degrees, or minus 235 degrees. Okay, so I hope it's clear. If we want to express this into cosine function, this becomes 1 over 5 cosine 120 pi t, from here, omega, minus 235 degrees. Any questions so far?
Excuse me, sir.
Yes, Elisa?
On the example with capacitor, I'm a bit confused. Never mind. I already figured out. Sorry.
Okay, you already figured out there. Okay, so this is from the previous slide. Okay, so based on that, we are now going to define new parameter, electrical parameters for AC state analysis when we have inductors and capacitance. So in DC, we only know about resistance. We know about resistance, and the inverse is called as conductance. And in AC steady state analysis, we will introduce the concept of impedance, which basically resemble that of resistance in this DC network, and admittance resemble conductivity, conductance in DC network. However, now there is a function, there is a factor of that omega, omega and J. So which J will change the phase angle. For each of the phasor components, the relationship between the voltage phasor and the current phasor is algebraic. We now generalize for an arbitrary two terminal element. So we have here a voltage source, having a magnitude of Vm, and here means basically this equals to V exponent j omega t, with the phase angle of theta V. And the current flows from this voltage source, Im, with the phase angle of theta I. Now we define here an impedance that belongs to this AC circuit. The input impedance of this circuit will be defined as Z. The input impedance equals to the voltage divided by I, or Vm with an angle of theta V here divided by Im divided by Im with an angle of phase angle of theta I. So the magnitude then of the impedance equals to the Vm divided by Im, and the phase angle of the impedance equals to the theta V minus theta I. Okay, so this is the magnitude Vm over Im. This one is the phase angle of the impedance. And this is phasor notation. The units of impedance is the same as the unit of resistance in ohm. So impedance is not a phasor, but a complex number that can be written in polar or Cartesian form. In general, the value depends on the frequency, this impedance magnitude, because it's basically it contains the factor exponent j omega t there. So Z omega equals to the impedance definition equals to R omega plus JX omega. This is basically, you have done this in the practicum, in the lab practice. R omega is the resistive component and X omega is the reactive component. And it has this J, it is shown as imaginary. So because it's not true power, as you have learned in the lab. Then Z, the magnitude of Z will be equals to square root of R square plus X square, and the angle, phase angle of Z will be equals to arctangen of X divided by R. Okay. So if we have element resistor, the phasor equation will be voltage equals to R resistor times current. So the impedance here will be voltage divided by I, which is the resistor itself. In inductive element, inductor, voltage equals to J omega Li. Yeah, voltage equals to J omega Li as we have derived in the previous chapter. So because then the voltage leads the current by 90 degrees by J. The impedance is voltage divided by I, so equals to J omega L. When the element is capacitance, then voltage equals to I divided by J omega C, right? Because the voltage lags the current by 90 degrees. So the impedance is defined as voltage divided by I, or equals to 1 over J omega C. Okay? So here let's whether to check whether KPL and KCL hold for phasor representation also. So here we have V1T, V2T, and V33. So according to KVL, the sum of the voltage along this path or this loop should be zero. V1T plus V2T plus V33 equals to zero. So VIT, well, VIT here equals to the Vm, the magnitude of that particular voltage in that component, exponent j omega t plus theta I, the phase angle of that ith component. I equals to 1, 2, 3. If we have parallel uh, branches, parallel impedances here, according to KCL, then the current entering here should be equals, entering this node should be equal to the current leaving that node. So minus I0 plus I1 t plus I2 t plus I3 t equals to 0. Yeah, so because the current is leaving, current leaving equals to current entering. IKT, the current at K branch, yeah, equals to the IM, yeah, the magnitude, K exponent j omega t plus phi k. So each of this impedance will create a phase angle shift, yeah, by itself. The K here for 1, 2, is for 0, 1, 2, and 3. So then using KVL, for this series network, Vm exponent j theta 1 plus Vm2 times exponent j theta 2 plus Vm 3 exponent j theta 3 all multiplied by exponent j omega t should be equal to 0. Yes, from here. So representing them in phasor, this becomes Vn1 with a phase angle of theta 1 plus Vm2 with phase angle theta 2 plus Vm3 with a phase angle theta 3 equals to 0. Yeah, V1, this is a phasor basically. V1 plus V2 plus V3 equals to 0. Yeah, because this is phasor already. So in similar way, we can show here that minus I0 plus I1 plus I2 plus I3 equals to 0. So here, because this is parallel network of impedances. Okay, so here the loop, the sum of the voltage along the loop should be 0. Here the branch, the current leaving and entering should be the same, yeah, equals to 0. The net. The components will be represented by their impedances, and the relationships will be entirely algebraic. So here are special applications. So impedances can be combined using the same rules as what we have learned for resistors. Yeah, using in resistors we have learned about series resistor, parallel resistors, right? When impedances are put in series like this, okay, so the current is the same current flows through both impedances. The series impedance ZS will be equal to Z1 plus Z2, or if we extend it to multiple, even more impedances, so ZS equals to sigma k times zk. When it is in parallel network, so the z parallel, if it is 2, will be equals to z1, z2 divided by z1 plus z2. Or if we have multiple branches, more than 2 branches, and similar like resistor, 1 over zp equals to sigma k from I from k equals to 1 until nth, yeah, the number of the branches, 1 over zk. Example here, we have the frequency of this signal in this network is 60 hertz. The voltage T here is 550 cosine omega t plus 30 degrees. Compute the equivalent impedance and current. So we have to then calculate the impedance due to this inductance, and then calculate the impedance due to this capacitance, and then add them because they are in series. Add the two impedances as well as the impedance due to the resistor. Afterwards, we calculate the current I equals to voltage divided by the impedance. Yes, yes. So here in resistor, the impedance of resistor basically is the same as the resistance value itself because resistor does not have J component. Yeah. Here for inductance, the ZL, the impedance due to inductance equal to J omega L. While in capacitance, it equals 1 over J omega C. Omega is from this frequency is 60 hertz, 2 times 60 is 120, 120 pi. Radian frequency, radian per second. So the voltage is expressed in phasor as 50 with an phase angle of 30 degrees. The ZR is 25 ohm, ZL is J times 120 pi times the inductance, 20 millihenry. ZC equals to 1 over J omega. Yeah, omega is 120 pi times the capacitance is 50 microfarad, 50 microfarad. So the inductance, the impedance to the inductance from here is equal to J 7.54 ohm, while the capacitance impedance equals to minus J 53.05 ohm. Zs, the total series impedance, will be equal to Zr plus Zl plus Zc. Yeah, 25 here is the resistance, while the components with J will be equals to the reactance. So we can just add up, yeah, J here, J 7.54 minus J 53.05. So this becomes minus J, the difference of this, yeah, 45.51 ohm. Calculating the current, voltage divided by the impedance, right? Voltage is expressed as this one, 50, the magnitude 50 with a phase angle of 30 degrees divided by the current. Current is this one, 25 minus J, 44, 45.51. Now we see here that the denominator, the upper part is expressed in phasor, while the lower part is still in complex form. So we have to transform this lower part into phasor form so that then they will be easily solved using complex algebra. How to find the phasor of this? So we have, yeah, this can be expressed like this. Where does it come from? So it is equal basically to the magnitude, yeah, the magnitude of Z series magnitude with the let's say phi. So where does it come from? So the magnitude comes from the square root of 25 square plus square root of 45.51. Okay, so this, please calculate. I think this should be, the value should be this, will 51.93. Yes, we can check actually. Ini 25 how to square 25 square plus 45.51 square equals to 2,696. Then this is square root of this. Yeah, more or less about 51.93. Yeah, 51.93 is the magnitude. So then the angle comes from from the arctangent. The angle here, the angle for this is calculated from arctangent of this j, which is negative, right? Negative 45.51 divided by 25. So let's try calculate. Those who have calculator, please also can calculate with me. So minus 45.51, 45.51 minus divided by 25. So we have minus 1.804. So then arctangen of this. How to do arctangen? Okay, very difficult. Which is just minus 61.22. Yeah, it's a minus 1822. Okay, that's correct. Yeah. So the angle that we will obtain is this angle, minus 61.22. Okay, so this is how we convert from a complex notation like this into a phasor notation. After we convert it into phasor notation, then it will be easier to calculate. So the magnitude of a current will be 50 divided by 51.93. The phase angle will be 30 degrees minus 60.22 degrees. Okay. Okay, so I have to erase first this part. Okay, so 50 divided by 51.93 will be equal to 0.96. 30 minus 61.22 equals to 30 plus 61.22, or 91.22 degrees. So if we express this back to cosine or sinus sinusoidal function, is equal to 0.96 cosine 2 times pi times the frequency 60 hertz, which is 120 pi t, plus the phase angle 91.82 degrees ampere. Okay, it's clear, yeah? Any questions so far? I think it's quite still easy, yeah, not that difficult. Okay, let's now try here. We have an example. Capacitance is in parallel with resistor and inductors. The inductor is in series with the resistor. If the voltage of the source is Vt equals to 120 sine, 377t plus 60 degrees, and find the current now. So what do you do? What you need to do is to find the equivalent impedance of all this. How to find that? You find first ZC, the impedance to the capacitor, ZR, impedance to the resistor, and ZL, impedance to this inductor. The ZR and ZL will be in series, as you just add them up. That this Z series, equivalent series, will be in parallel with this ZC. So you find the equivalent impedance by using the parallel impedance formula. From there, then finding the current is by dividing the voltage by the impedance. Omega is known to be 377. So this is not in hertz, so this means in radian per second. So the voltage can be expressed as, since this is in sinus, be careful. In phasor is always the representation of cosine signal. So from sinus, you have to convert first, re-express first as cosine. In order to re-express in cosine, you have to add phase angle 90 degrees, minus 90 degrees, because sine function is basically uh, lagging cosine, a cosine function that lags 90 degrees. So the phase angle will be 60 minus 90 degree or minus 30 degrees. Okay, then the ZR it is equal to 20 ohm, no imaginary component. The ZL equals to J omega L. J times 377 times 40 millihenry equals to J 15.08 ohm. The ZC equals to 1 over J omega C, or uh, wait, correct, right? Yeah, 50, yes, yeah, 1 over J omega C. The formula for the impedance for capacitance is 1 over J omega C, or equals to negative J over omega C. Yeah, so you could put also the J in the denominator, in which case then you would need to have negative. Yeah, so actually here the capacitance here, this it comes. So actually this is ZC equals to 1 over J omega is 377 C times the capacitance 50 microfarad, or equal, if you multiply with J over J, okay, J times J becomes negative J divided by this value, and this value is 77 times 50 times 10 to the power of minus 6, and basically that we will have this minus J 53.05. Okay, then the equivalent of the whole impedance here will be equals to ZC in parallel with ZR plus ZL. So Z equivalent will be equals to this, yeah, 30.963 with a phase angle of 9.239 degrees. The current then will be voltage divided by the Z equivalent, which will be equals to 120 angle of 9 minus 30 degrees divided by 30.93963 with an angle of 9.239. So the magnitude will be 120 divided by this, yeah, equals to this, yeah, more or less. The phase angle will be minus 30 degrees minus 9.239 degrees. So equals to minus 39.924 degrees. The unit is in ampere. Okay, clear, yeah? Okay, now what about the admittance? As I mentioned, admittance resembles the concept of conductance in resistive network. Yeah, in resistive network, it is similar like that. But admittance is for AC steady state analysis. So the Y is equals to, which is the symbol for admittance, equals to the inverse of impedance, or 1 over Z. And this can be expressed as G plus JB in Siemens. While Z, remember, is expressed as R plus JX. Yeah, in the previous slide, if you remember, or I will just rewrite it here again. The Z equals to R plus JX. R is the resistance, the real part of the impedance, while X is the reactance, yeah, or the imaginary part of the impedance. So similarly, admittance is also a complex entity. So is expressed as G plus JB. G we have learned in semester 1, right? As conductance, basically is 1. It is 1 over R plus JB. B is the susceptance. Susceptance is the inverse of reactance. So if Y equals to 1 over Z, yeah, or the inverse of impedance, so equals, it means if we substitute Z with R plus JX, this equals to 1 over R plus JX. Then, in order that we don't have imaginary entity in the denominator, we multiply with its conjugate, yeah, both numerator and denominator. So it multiply by R minus JX divided by R minus JX, which this equals to 1, right? So the denominator part, the denominator part becomes R squared plus X squared. The denominator part becomes R minus JX. So from here, the the real component of the admittance, yeah, the real component of the admittance is this part. Well, the or the conductance basically, while the imaginary component of the admittance is this part, minus G, which becomes the B. So this is the susceptance, and the real part here is the conductance. So the G equals to R squared, R divided by R squared plus X squared, and the B, or the susceptance, equals to minus X divided by R squared plus X squared. Okay, then based on that, we can summarize now that for resistor element, the phasor equation is, yeah, the Ohm's law. Voltage equals to Ri, although this is phasor, yeah, so equals to Vm exponent J theta. The impedance is Z equals to R. Yeah, impedance is voltage divided by I. And here equal to R. The admittance is current I divided by voltage. Yeah, equals to 1 over R, or G, the conductance. In inductance, the voltage equals to J omega Li. Yeah, then the impedance then will be equals to this J omega L, because this equals to voltage divided by I. The admittance equals to I divided by V, yeah, which is equals to 1 over J omega L. This is the inverse of this. In capacitance, it is opposite of inductance. Yeah? The voltage is expressed as 1 over J omega C times I. So the impedance is voltage divided by I is equals to 1 over J omega C. And the admittance equals to I divided by voltage equals to J omega C. Okay, any questions so far? No question, yeah, I hope it's quite clear. Then parallel combination of admittances is similar like when we calculate the parallel combination of conductance. Yeah? If it is parallel, then we just add up the conductance. So similarly, admittances YP equals to sigma K from 1 and of YK. Like this, if it is in parallel, the admittance here will be the admittance R due to this 10 ohm plus the admittance C, YC due to this capacitance. So here in this case, the YR equals to 1 over 10, right? 1 over resistance is 0.1 Siemens. And then the YC, the susceptance, yeah, the admittance of the capacitance here equals to 1 here. The formula is here. J omega, this is the impedance. Yeah? So this is the impedance. So it means the admittance just 1 over this value. 1 over this value, 1 over minus J1. Multiplied by J divided by J, this becomes plus, equals to J1 Siemens. So then the parallel admittance will be equals to 0.1 Siemens plus J1 Siemens. If it were series, then combination of admittances will result in 1 over ys equals to sigma of 1 over yk, the branches. Not the branches, the series admittance. So this is the same as conductance in series in resistive network. So like this, you have 10 ohm connected to interdictance of J 10 ohm. And so this, the admittance will be equals to 0.1 Siemens. The admittance is this is 1 over J10 Siemens or minus J 0.1 Siemens. Okay. The parallel admittance is calculated like this formula. So we obtain 10 plus 10 plus J10. Then from here, the ys equals to the inverse of this. The inverse of this. And 1 over 10 plus J10. This equals to 10 minus J10 divided by 200. So we separate from the real and the imaginary component. So this becomes 0.05 negative J 0.05 Siemens. Okay, any questions so far?